Thank you very much. It's okay if you digest in parallel, so that's fine. Yeah, I'm pleased to talk about characterization methods. So instead of focusing on modeling, this presentation is more on what kind of experimental techniques can you use to study OLEDs, the different processes going on in the OLED operation. At the end, so maybe this should be less than 14 minutes. I hope it's a bit shorter than the previous one. If we have time, I could give you at the end some, it's not a kind of a demo of the PIOS measurement platform. This is the user interface where we can browse through some measured data to show you what kind of data analysis you could do. But now, okay, the content of this presentation, I will describe a bit the concept of all-in-one, that we combine different measurement techniques in order to get a most complete picture of what's going on in the OLED. And I'll give examples of these measurement techniques for OLEDs. Of course, you can imagine that this kind of techniques can similarly be applied to solar cells. A lot of these techniques can be used for both types of devices. But I also brought 3 example case studies. One on polar OLEDs, meaning OLEDs which have a polar electron transport layer, where we see some specific signals in the measurements that we can explain with simulation. A second topic is the MIS-CLIF method, which can be applied to OLEDs as well. And a short last example is PIP device modeling, device measurement and modeling. So what we're trying to propose is, instead of going to different laboratory rooms, in one you measure the IV curve, in a second room or second instrument you do impedance spectroscopy, and in the third lab room you do transient electroluminescence. This would be classical, but now we propose to do all at once without changing cables and without changing contact resistance and different systematic errors. So the beauty of doing all from one device, from one instrument, is that the data is really comparable, and it's measured the same day, the same hour, and not in a different day and different humidity and so on. So the comparability of the data is very good. And so it's first, after fabricating the device, you set up the protocol of which measurements you want to carry out, and then you start to you press the start button, and then the whole sequence of experiments is carried out, and then you can have a coffee, come back, and you have lots of data, and then you can start thinking about what does the data mean. So you spend more time with thinking about the physics and not about how to carry out the experiment. So this gives you an overview on typical measurement techniques. On the upper left, we see an impedance spectroscopy measurement where we sweep the frequency of the applied AC voltage, and we plot, for instance, the capacitance frequency. Then photo-CLIF is known from solar cells, but I will show a modification of this technology for OLED characterization. Then we have capacitance voltage. I mentioned it in the modeling talk already. Then dark injection transients. This is mainly a method suitable for hole-only, electron-only devices. But sometimes even in the polar device you see a very similar response. Then we have transient photovoltaic charge extraction. That's more for solar cells, so let's skip that. But JV curves, that's an OLED. Then for OLEDs as well, we have transient electroluminescence, where you can look at the onset, the time of light output after voltage turn on. This delay time is interesting. And then these two are for solar cells more. Intensity modulated photo current spectroscopy, intensity modulated photovoltage spectroscopy. Now, after you've done a measurement, of course there's always 2 categories of analysis. Either you play around with simple formulas just to detect a peak, and from the peak position assign, let's say, a dynamic transient, take a peak position, assign a transit time, estimate mobility. So we call that basic processing. Another example is Mott-Gurney fit. So if you have space charge limited current, then the current should scale with the square of the voltage and the inverse, cubic inverse of the thickness of the device. So here you see an example where the black line is the measured data, and in the blue range of voltages you can carry out the fit automatically with this interface, and then you can store the extracted mobility parameter here, store it in a database, and go on with analysis. That's one example of a basic post-processing where you don't have to use drift diffusion modeling. Just apply the formula that is shown here. Another example is a one diode model fit, which is shown here in a logarithmic current scale versus voltage. The formula is not shown, but we see here the equivalent circuit of this red model. So the red curve is an analytical formula describing the diode behavior of this device. That's also a kind of basic post-processing. But already from this kind of basic post-processing, you can extract, for instance, the series resistance here. Have an idea for series resistance, also for parallel resistance to the device. So there are certain measurement techniques that you just do because you want to know the series resistance. As you know, or maybe I've indicated that the series resistance influences a lot the dynamics of the signal. So if you have a lot of resistance, the signals get slower, and that's happening in the measurement. And if you want to successfully describe this with a model, you also need to know the value of the series resistance to put into the model, meaning the drift diffusion model. You need to have a good estimate of these series resistance, for instance. Then we also have fitting with equivalent circuits. This is implemented as well. You can select from different RC elements and different template circuits that you could fit your data to. But because we prefer to do more physical modeling with drift diffusion modeling, we don't advertise it too much. So this is just for information. Here we have an example of basic post-processing where the PIO software, this is a photocell experiment. I think it's a solar cell example, but the peak position is automatically detected and translated into a mobility value. And for here, I think it was a sweep of the light intensity. So it's a light pulse shining on the solar cell, and a voltage ramp extracts the carriers, and the extraction time, so the peak position is the extraction time that can be related to a charge mobility inside the active layer of the solar cell. So this also gives you an estimate of mobility, and you can already tell that you would expect to get always the same charge carrier mobility regardless of what light intensity you pulse the solar cell, but sometimes there is some tendency that the values change a bit, and then you can decide, oh, let's just take the average value and store it into the database. That's an example. But again, this is basic post-processing, which does not capture all the physics. So we have made some publications where we were able to simulate the full curve by drift diffusion modeling rather than just assigning mobility to the peak position. So that's then the next category is not basic. Yeah?
About charge mobility, because in sense of you are using charge mobility, but you haven't told us which charge mobility you are using, because there are several ways to analyze that, and you are receiving different results. So I understand here you are using CELI, so in the sense of it's also best to use those results from CELI, or is there a comparison between those two softwares?
Yeah, it's indeed, as you know, in the physical model you need electron mobility and hole mobility. And some of these experiments you don't even know for sure, do you see the majority carrier now electrons or holes? So it's really not so clear. But let's say if this here is a PIP device, a hole-only device, where the IV curve is probably dominated by holes, then you could assign this mobility to the holes and then use the same hole mobility value in the drift diffusion model afterwards. So it's actually possible after if you believe this kind of estimate of mobility, you can take this estimate as a starting point for the later fitting. So if you have here now, if you then try to simulate the data with ZFOS drift diffusion simulation, you could use those estimated values as starting points for least square fitting. Because, as you said, the drift diffusion model needs a mobility parameter for electron and hole for each semiconducting layer. And so you need to do some least square fitting to adjust the model to the measurement. Yeah. And I will maybe mention here, yeah, this adjustment of model parameters to the measurement is done in an iterative way. So at the beginning we have here an error. The error measures the difference between the experiment and the model. And for each iteration step, the error gets smaller and smaller. And at some point it stops if the accuracy is good enough. And you see how each model parameter evolves. In this example, we have the whole mobility. We have an initial guess, but then the value is updated. We have photon to charge conversion coefficient and electron mobility here, which also moves a bit while the fitting advances. So for each iteration step, another drift diffusion simulation is carried out, and the error is evaluated, and hopefully this will monotonically decrease here. This is then what we call global parameter fitting, because the error that we define here, we can, for instance, include current voltage curves, but we can also include transient signals. In fact, so you can include multiple curves, not just one IV curve, but also impedance curve or transient curve. And once the fit is good, the question is, what is a good fit? First of all, the error should be small between model and measurement. And second of all, the model parameters should not be correlated among each other. And I will get to that in a moment. Yeah?
No, because I will use it to talk about what I'm asking. So, but this is for one layer system or one active layer. So for one device, we are not measuring mobility of one device, but on the one layer we are simulating or adjusting.
Now, when we do this ZFOS pios fit, then the model includes all the layers.
So we are adjusting all the whole mobilities and electron mobilities for every layer.
You can choose. I mean, some parameters maybe you trust. Oh, this value is from the literature, alpha NPD. I take whole mobility. Okay. Yes. Yes, it's good to be skeptical, because even the way you process a certain material may lead to different properties. But you can choose which parameters you keep constant and which parameters you let adjust automatically for a better fit. Yeah. And this is an example we published for OPV, organic solar cells. So we have current voltage curves at 3 different light intensity of the solar cell. The black is the measured curve. Then we perform the second and the third and the fourth experiment. So we combined 4 data sets of 4 different experiments: steady state, light pulse, dark CLIF, and photo CLIF. Dark CLIF means that you apply voltage ramp without prior light pulse, without any light, but photo CLIF you apply a light pulse and then a voltage ramp to extract the photo carriers. And so these are in total 12 curves, measured curves, and then the fit result is the list of parameters here. Well, some parameters are related not to the semiconductor device, but to the measurement setup. For instance, the series resistance of the ITO or illumination intensity, and some other parameters. So what we recommend usually is to try to determine the simple parameters first before doing the global fit. So series resistance has been determined in the first step. And then the other parameters, mobility and injection barriers at anode cathode, are the result of the fit. And now what is a good fit? You see here an example of a correlation matrix. A correlation matrix means that if you have 7 parameters that you fit simultaneously, we list them on the on this table and also vertically. And the diagonal means that each parameter is correlated to himself. That's clear. But for instance, this value here, the hole mobility is strongly correlated to the electromobility. So if the number here is close to 1, that's bad. Ideally, we want to have 0, no correlation among the parameters. And you see, if you only include current voltage curves, meaning just these 3 curves here, and then don't include the other data, then you get strong correlations of the extracted model parameters. All these numbers are quite big. And alternatively, if we choose JV, light pulse, and photosilic, so all the 4 different measurement techniques, then we get smaller correlations. So here we now have much reduced. Well, there is still some correlation, but it's significantly reduced compared to this case where you only include current voltage curves into the fit. So that's the first message, is you get better fits if you include more than JV, if you include pulse data or even impedance spectroscopy data. So this kind of methodology you can apply to OLEDs, and at the end I have an example of a PIP device. And yeah, this is actually an OLED example as well. So this is a kind of 30-year-old OLED type, yeah, this Kodak OLED type, where you have, at reverse bias, you have a geometrical capacitance value. So this, in this number here, 15 nanofarad per square centimeter. That's the geometrical capacitance, so the parallel plate capacitor. If you believe the OLED is empty, no carriers inside, then this would be, for the given thickness of organic layers, this would be the expected geometrical capacitance value. And you see here that one curve is measured and the other one is simulated. Okay, they're both in red. It's a bit unfortunate, but the thicker one, that's the measured curve, and the thinner line is the simulated curve. You see they don't fit yet. So instead of doing a fit, there's also an option to do parameter sweep. And you see here a slider. So if we now change the value of the polarization chart sheet, I will get to that later on. But if we change the value here of this quantity, you see that the simulation moves to the left, the curve moves to the left. So basically you can also manually adjust the parameters by sweeping the values until it fits. That's the alternative to using an automatic least square fit. Yeah, that's capacitance versus voltage for a fixed frequency. Here it was used 1 kilohertz as a frequency for this measurement. Instead of keeping frequency and sweeping voltage, we can also do a frequency sweep. So this is now the first experimental type that I'm going to explain. And so the impedance spectroscopy, I briefly mentioned it in the modeling part. We apply an offset voltage and an AC voltage amplitude at a certain frequency. And the result, we can either quantify admittance Y or impedance Z. They are just the inverse of each other. And if we look at the admittance Y, we split into conductance and capacitance. Now that's a well-known method to look at the current response to the voltage excitation. Now over time we have played around with the measurement techniques, and Martin Neukom, my colleague, he has implemented something new. So instead of looking at the current response to the voltage excitation, he looked at the light output for this AC voltage modulation. So by changing the frequency of the AC voltage, we look at the light output or the current efficiency, meaning, so this is also a complex quantity. Instead of looking at the complex current, we can look at the complex light output, and we see that there is a certain characteristic frequency above which we don't see light output. This is to be expected because the carriers need time before they recombine to cross the layers. And so this is just another way of looking at delayed EL turn-on. So it shows that you have many different options of making new experiments. You can even user-define your own experiment by defining a certain voltage or light signal. And this is an example of it. Now the capacitance voltage method, well, it's well known, for instance, for Mod-Schottky analysis. There I already mentioned that in reverse bias you expect geometrical capacitance, and then if the applied voltage overcomes the built-in potential, then you start injection, and then you have charge penetration, which leads to an effective increase of capacitance. So that's expected. So Mod-Schottky analysis would typically look at the slope here and assign density of dopants. So that's one way of analyzing this data. So there are routines implemented that allow you to extract Mod-Schottky doping density. That's an additional feature. Now here's an example of OLED degradation, which was monitored by using capacitance frequency and capacitance voltage response. So the three OLEDs were, the first OLED was fresh, 100% light output at the given current density. Second OLED was already stressed and only emitted 90% of light, and one was further degraded to only emit 75% of the initial brightness. And you see that they have a systematic signature in these capacitance frequency and capacitance voltage curve. For instance, here we see that the capacitance voltage curve, which I just mentioned before, that the peak position is related to overcoming the built-in potential. So that if the peak shifts on the voltage axis, it's a sign that the injection barriers have increased. So if we look at the aged OLEDs, the fresh one was the red, and for the aged OLED, the peak has shifted to higher voltage. So it means that charge injection starts at higher voltage when the OLED has started to degrade. That's one signature of degradation, and in capacitance frequency, there's another systematic change that was already studied by the Britting group. So that's an example of applying impedance spectroscopy to fresh and aged OLEDs. Now let's switch to, so we started with a little bit of JV curve, a bit of impedance spectroscopy. This is now another experiment, dark injection transients, DIT. Another abbreviation is transient space charge limited current. So we need a device that has ideally just one type of carrier and a well-known thickness across which current flows. We apply a voltage step, and we look how long it takes until the local peak appears here. And here, interestingly, there is a first initial peak that is more an artifact than a sign of charge transport. It's namely the RC time effect, that the RC will lead to a strong increase and quick decay. So if you have good devices with a short RC time, then you indeed will discover the peak that you're looking for. If the RC time is too big, then it will be hidden in this first tail. But the formula to apply is take the time position of the peak, multiply by the net applied voltage, and then use this simple formula to estimate the mobility. This can be done here with this data. I think that's an example of alpha NPD. It was about 1,000 nanometer thick alpha NPD sample, and we have seen a nice signature here of the expected curve shape here. The initial peak is due to RC time, but then the real transit time peak shows up. And as expected, for increasing voltage, the current goes up and the transit time gets shorter. For higher voltage, you have a higher velocity. Even at constant mobility, the velocity is higher, so the transit time is shorter for higher voltage. This behaves reasonably. And this is a direct comparison of such data, dark injection transients, with transient simulations, where we see that it behaves very similar. We have the logarithm of the current plotted for both the measurement and the simulation. And then, okay, that was without light emission. But now if you have a bipolar device, if you inject carriers from anode and from cathode, then you will start, for the same voltage pulse, you will then have an electroluminescence rise. And you will notice that there is a delay time or onset time here until the first photons emit from the OLED. And usually there's a certain shape of the EL rise. It can be a fast rise and a slow rise combined. And the similar formula that we have used here to estimate the mobility from the dark injection transient, similar formula but not with this SDLC prefactor, can be applied here to estimate an effective mobility of the charge carriers, which is responsible for this delayed onset here. And there again, the valid criticism is we don't really know what is this mobility, can be assigned to electron or hole, or maybe the sum of the two mobilities to describe this delay. This is real data. That was just a sketch, but this is real data of an OLED where, sorry, the voltage scale is missing, but for increasing voltage, the onset time moves to shorter times. As expected, higher voltage, higher velocity of carriers, so the first photons come out earlier. And this is normalized light output, so it's scaled to 1. So the lowest voltage will reach the steady state much later than the high voltage case. So this is typical. But then you could define a threshold here to define the time delay. This is done automatically by the PIO software. You can simply assign here a threshold current for which to use for the mobility estimation. So this is an example of 3 different voltages, the turn on. And on the right you see for 1 voltage, we get 1 value here of a mobility that is automatically extracted by this simple formula. Now let's look at a bit more closer at this typical signal. The EL turn-on can be fast and slow in 2 components, and it turns out that there is a sound explanation for this. An old publication from Pinner et al., which studied polymer LEDs, so those were just single-layer OLEDs, just a single semiconductor layer. And you see also there that turn-on has a steep and a kind of slow component, but you can only see them if you take the maximum EL light, 1 minus the signal, so to have a data that looks like a decay. So the same turn-on data is plotted differently such that it looks like a decay, and then you can extract the 2 exponential components of the dynamics. And the steep rise will be a steep drop here, and the slow rise here will be a slow drop here. So these 2 time constants that come out were already back then assigned to electron and hole mobility in the emissive layer. And we have put this under test with our software also to simulate an OLED where the emission layer has electron and hole mobility which are not the same. If they would be the same electron hole mobility, then you couldn't resolve the 2 time constants. But if they are different, then you indeed see in the model we have here 2 time constants in the model. And in fact, if you do such a measurement and you plot it differently, namely like the maximum minus the signal, then you actually get this kind of shape. So you have a fast time constant and slow time constant. So that's the turn-on dynamics from which you could estimate electron hole mobility in the emissive layer. Just the emissive layer, regardless whether there is additional layers. Yeah. Now let's look at the decay. if we turn off the voltage, then we still get emission from the excitons which are still there. That's one reason. The other reason could be that there are still electrons and holes which walk around and recombine. In the previous presentation, I've shown this example of a Reinecke publication also, where he argued that the electron holes go out and make delayed recombination. But the simple explanation is that just the excitons decay mono-exponentially. If this is the case, mono-exponential decay after turnoff, then you see a nice straight line in the log of the intensity versus time. And here, this was a phosphorescent OLED, where the time constant is 2 microseconds, which is reasonable for this kind of phosphor OLED material. Yeah, it's of course sometimes it can be more involved. In this publication by the group of Nates, they have actually slightly modified the OLED structure in order to modify the optical feedback, the Purcell factor, and then the decay time after in this, the decay constant changed with the device structure. So you can even infer from the decay constant, you can infer how strong was the optical feedback of the cavity. So that's an interesting cross-check about the optical model as well. And here we also have this OLED degradation study, where the fresh OLED 100% light output had a certain decay here in log intensity. So it's not really mono-exponential, but interestingly, for the degraded OLED, only 75% light intensity OLED, the decay was faster. So what it means in the degraded OLED, there was an additional decay channel, maybe non-radiative decay of species. We don't really know what, but we see a signature that the decay of the excitons is accelerated. So it could indicate that not the charge transport layers have degraded, but also the emissive species have additional competing channels to decay non-radiatively rather than radiatively. So you see there's a systematic change between fresh and degraded OLED. And then we have two other examples of where we varied the temperature. So we put the OLED in this cryostat chamber, measured with Pio's instrument, and we varied from 230 Kelvin to 300 Kelvin. This first OLED, I think we varied the temperature. So the high temperature is the red one, and the noisy curve is at low temperature. So we have less light, but the dynamic of the decay is independent of the temperature of the device. That's the left example. And on the right, we see a distinct change. So the decay of electroluminescence changes. This is kind of TADF-like, where at high temperature, we have a faster decay than at low temperature. Yeah. So you can get some systematic data with the real OLED. You're not doing an experiment in photophysics optics lab, but just directly OLED, put it in a small cryostat chamber, and you already get a lot. Now let me comment on the 2 or 3 case studies. First case study is on polar ETL materials. And this is again the 30-year-old OLED with ALQ3 as a ETL layer. We know that the ALQ3 molecule is a polar molecule, and it turns out that after deposition on the substrate, it can preferentially align, or there's a spontaneous orientation polarization, which results in an effective sheet charge density, which is negative at the interface to the hole transport layer and positive at the interface with the cathode. And this was kind of already observed a long time ago, but we have now managed to quantitatively describe this effect with simulation. So we have indeed assumed these charge sheet densities. And this property of polar ETL is not only for ALQ3, but also for BFN, BCP. So many electron transporting materials have this property. It should be taken into account if you want to make a quantitative OLED model. You should check of signatures of polarity of layers. So we managed to reproduce this. And the question is, of course, also how does this property affect the device performance? Is this sheet carrier density at the cathode, is this an advantage for efficiency of the OLED or not? So let's first look at the experimental evidence. For reverse bias, we have a geometrical capacitance. But then depending on the ALQ3 thickness, there is a very interesting increase of capacitance. An increase of capacitance with respect to geometrical capacitance always means that there is one carrier type already flooding into the device and maybe accumulating at a certain interface, which basically makes a parallel plate capacitor which is thinner than the total device. That's why the capacitance goes up. So that's qualitatively the explanation here. I'll show some sketches as well. But already here we see that the set for simulation can nicely reproduce the scaling of this signal with thickness of ALQ3. So the new value, let's look at the blue dashed. For this thickness, 120 nanometers of ALQ3, we see that this level of capacitance corresponds to the capacitance of the ALQ3 layer. What we have observed is that the holes will already enter the device, pile up at the interface. Because we have so many free holes that pile up, they will define a capacitance across the ALQ3. So let's look at this here in the sketch. What I just said was that if we are at the right voltage, namely below built-in voltage, but above the transition voltage. What is the transition voltage? We call it the voltage at which the capacitance rises here. But this depends on the thickness of ALQ3. But so if you are in this regime of this elevated capacitance value, if you are at that specific voltage range, then the band diagram looks such that the electrons would have to go uphill, so they will not be injected, but the holes, they can go, the holes, they want to go uphill in the band diagram, so they are injected, and they pile up here at this interface, and this defines the higher capacitance value. If you go much lower in voltage, then the band diagram, this is simulated. The upper diagrams are simulated, the lowers is just a sketch, but they coincide nicely. You see that if you go strongly negative in voltage, then you just pull out all residual holes or electrons, and only in the intermediate range you have one carrier type, namely the holes. If you go higher than the built-in voltage, then you start to inject the electrons as well. As you can see here, the electrons can now they can go downhill, they are injected, and the holes can go uphill. So now it's a bipolar operation, but in this intermediate voltage regime we have only holes. And this is nicely visible in this measurement. As you can see, it's nicely reproduced by the simulation. And this is what we published last year. We published a simulation result that nicely corresponds to the measured curves and proves that indeed the polar ETL layers can be modeled by charge effective sheet density of carriers at the ALQ boundaries. And we also studied what would happen if the polarity would be flipped. There are some materials that have an opposite polarity in after film deposition. And in fact, that is not good for electron injection at the cathode. But for ALQ3, it's beneficial for injection. Okay. This kind of CV capacitance voltage signal that I just discussed was for the fresh OLED. So the blue curve, so starting from geometrical capacitance, then at the threshold voltage or transition voltage, we have an elevated capacitance, and then at turn-on voltage at 2 volts, the capacitance goes down. That's typical for bipolar injection. Then the recombination starts and the capacitance goes down. But the interesting thing is here that the transition voltage shifts to higher voltages after prolonged degradation, prolonged stressing. So we have just driven at constant current, and we see that this signature goes to the right. And one way to explain by modeling is that the effective sheet carrier density at the boundaries of LQ3 is diminished. It gets smaller. So if this interfacial charge, if we reduce it, then indeed, as in the experiment, the transition voltage shifts to the right. So it could be a qualitative description of during the initially preferentially oriented polar layer, after degradation, it's becoming more isotropic again, and this effect kind of disappears after degradation. So that's our qualitative explanation. And in terms of degradation, you can imagine that this kind of combined measurements of steady state, transient, and even impedance, you can repeat it at different degradation states. This was a study done with an organic solar cell in a climate chamber at high humidity, high temperature. Unencapsulated OPV, so degradation happened within 1 or 2 days. So every 10, 20 minutes, we remeasured. We see the red curve is the typical capacitance voltage curve of any organic semiconductor device. We have a CV peak in the fresh state, but then during degradation, something strange is happening. At the end, we have a very high capacitance here, and even a constant capacitance. So somehow there's a blocking behavior. There are charges injected, but they cannot penetrate further. And we have quantified all this in a complete picture and found that the aluminum cathode starts to oxidize from the boundary. So the humidity penetrates from the side, and effectively the solar cell degrades from the boundary to the center. And yeah, this is a nice comprehensive study where we combine these measurements and modeling. Okay, but let's go back to the OLED. For the OLEDs, the CLIF can also be applied. So what is CLIF is defined as charge extraction with linearly increasing voltage. So the signal looks like this. We apply a voltage ramp. We start here in this particular case, if we want to do OLED characterization, we need to have charges inside. So we need to have a voltage higher than the built-in voltage. Otherwise, we cannot extract any charge. So we apply our, I have to correct myself. Now we are again looking at the bilayer OLED with ALQ3, and we just learned before that for this particular OLED, due to the polar ETL, we already have charge injection below the built-in voltage. So we choose a voltage in this range, and then we have already selective carriers. We only have holes in the device. There are no electrons, so we can make a charge extraction experiment with only having holes. Yeah, now here's the picture. So we have the initial state here. At this voltage, we have the holes in there, and then at certain time, we make a negative voltage ramp. It means we pull out with the field, we pull them out again, and we expect a current peak corresponding, the peak position corresponding to the mobility of the carriers. And so it means that this strange effect of polar ETL allows us to make a mobility determination experiment which clearly can be assigned to holes and not electrons. We know here that we only measure the holes. So we can then apply the standard or kind of standard CLIF formula, but we will adopt it a little bit because this CLIF formula is for single layer, but now we have a bilayer. But anyway, also you should notice that we can not only from the peak position of the current we get the delay time and thus the mobility, but from the integral, if we integrate the current in this peak, we can estimate how many charge carriers were in the OLED before we extract them. So we measured mobility and the carrier density. So this is shown here. The actual measurement looks like this. We can also we can choose different initial voltages here. And for moderate voltages, we have the blue curves and the small peak. But if we increase the voltage, we also have more holes flooded in the OLED, and therefore the integral of this peak here will lead to a higher charge density that was inside the OLED. So we can quantify how many holes were accumulated at this interface. And moreover, we can estimate the mobility due to the peak position of this transients. But we have to slightly modify the formula because we have a bilayer device and we only look at the HDL layer transport. So this is just published a few weeks ago in Journal of Applied Physics, where you can read more about this methodology. So it's a new method which can be applied to OLEDs where we have a polar layer and thus allows us to make whole mobility determination. Yeah, this is some more about this. Interesting is that usually you would expect for CLIF in an OLED, in order to get a selective carrier to only have, you could only expect it from MIS devices, metal insulator semiconductor, where the insulator makes sure that the other carrier type is not injected, but only from the S side, not from the metal side. So this means that MIS CLIF originally would be, people thought you would have to do an insulator layer here to avoid electron injection. But now, thanks to the polar ETL, we can also avoid electron injection and only have whole carriers there. And this is nicely confirmed by the simulation here on the right-hand side. Okay, I've already shown a few measurements where we vary the temperature, and we're typically just using a small chamber cooled by liquid nitrogen, and then we can systematically study what's going on with temperature. For example, this capacitance voltage curve, again, the peak position is related to the built-in potential. So if this energetic barrier for injection from the cathode, from the electrode to the semiconductor, at lower temperature, this barrier becomes effectively higher, and therefore the peak position moves to higher voltage. So that's also nicely as expected. For lower temperature, charge injection starts at a higher voltage. That's the measurement on the left. Sorry. Is it different frequency? Sorry, this is, I thought it's different temperature. But we have a similar graph for different temperature, I'm sorry. Yeah. But, no? No, this is the temperature. I see frequency is the same, but the temperature, yeah, so. Okay, thank you for correcting. It is indeed temperature dependence, and on the right, it's a simulation of capacitance versus voltage, also as a function of temperature, and it behaves very much the same. So with this kind of measurement, you can even try to validate the charge injection model in the software, whether this behaves correctly. And this bilayer OLED, we can also vary the temperature and look at the thermal activation, where we see that the geometrical capacitance value and the second plateau of ALQ capacitance is again connected to this hole penetration. If the capacitance is at this level, we have already holes penetrated, and as expected, this will depend on the temperature. At low temperature, we can no longer inject easily the holes into the whole HDL, but at high temperature we can. So we can even study thermal activation of hole injection into the HDL. Okay, and yeah. Now the last case study is a very simple device, PIP, which has been popular to study charge transport in a monopolar device. And this particular one is fabricated by TU Dresden in the Mostofos project. We have here PIP device structure with four different thicknesses of the HTL layer. And at the boundary, we have p-doped layers for a good injection. And you see that the current voltage curves for the three devices, actually the thinnest thickness is not shown, but the other three thicknesses are shown. And then the capacitance frequency curves also. We have a kind of a increase of capacitance at low frequency. And what you see here is a global fit. So we applied fit across all these 6 curves, 3 IV curves and 3 capacitance frequency curves, and tried to extract one set of model parameters. So here are the key parameters for this device. We have for the HTL layer a 0 field mobility and the field enhancement coefficient. And then for the p-doped layers we have doping density and also a hole mobility in the p-doped layers. There we have high carrier density, so there we can allow for a different mobility of the holes. And okay, that's the fit, how it can look like. And then with this model parameters, we can now simulate further curves like capacitance voltage, because for the fit we have used capacitance frequency, but we can predict capacitance voltage and conductance voltage for the 3 different thicknesses of HDL. And you see that the curves that are, the thin lines are the simulations and the thick lines are the measurements. We have quite a good agreement, so it's possible to simulate this 3-layer device. And then you can also visualize the cross-section. How is the free carrier density of holes in the p-doped layers? How does it behave near the interface with the intrinsic layer, both at 0 voltage in green and at high voltage in blue? And we can also take profiles at different frequency to understand why do we have an increase of capacitance. Okay, that was the last case study. And yes, I hopefully have shown you that comprehensive measurements are useful and very interesting to study the device physics. And if you have a minute, I could show an example